quick introduction. I'm Praveen. I work as a staff developer advocate at Hasura. I've been working with Hasura for a few years now, so I have seen the evolution of GraphQL, seen the evolution of various technologies over here, the data access patterns that have evolved, and I'm happy to share some of these experiences today as well, in terms of Elasticsearch in today's context, but also broadly about the GraphQL, Supergraph, and Subgraph as conceptual evolutions. Like quick agenda check. We'll be looking at the architecture and seeing how Elasticsearch can be used as a subgraph, and then how can it be part of a larger supergraph in an organization. And then we'll talk about the API automation part of Elasticsearch, the various capabilities of the API, how rich is the API, what are the possibilities that you can do, joins across different sources. So we'll look at all of that capabilities. And we'll also talk about performance. How is Hasura able to do high performance APIs on Elasticsearch? And we'll talk about various examples where you query one index in Elasticsearch, where you join multiple indexes, or probably when you join across a few data sources, right, as well. So we'll see how architecturally Hasura is able to do this with high performance. We'll also look at security patterns for Elasticsearch data access, but also this will broadly apply for any data source that you connect to Hasura, right? And finally, I'll do the demo, and I'll talk about all the API capabilities, and I'll showcase connecting the API to Elasticsearch, right? Quickly, architecture, we have like broadly Hasura instance in the middle, but then you have data sources, right? You can have Elasticsearch, you can have an external API, you can have other databases that are coming in. So you typically connect your databases with Hasura. Hasura has like a bunch of metadata about your data sources, and it'll expose APIs for your consumers. It could be your web apps, your mobile apps, or any other clients, or internal apps, which require a HTTP endpoint to consume, right? So Hasura exposes GraphQL. It could also expose a REST API, and in the future, gRPC or whatever, right? So you have input data sources, output different formats of APIs as you would like to expose to your clients or consumers, right? So that's broadly the architecture. We'll talk about how Hasura's metadata is critical and makes all of this really easy to use and get started. Which brings us to domain modeling and how Hasura actually fundamentally works, and how is it different from your DIY GraphQL or DIY API modeling as well, right? So the broad idea is that you create like rich abstractions, irrespective of whatever data source that you have, right? It could be a database like Elasticsearch or like Postgres or Mongo or whatever, right? And you could also have an external API which has some models. Could be a REST API or a GraphQL API, but the idea is that you create like a model level abstraction on top of all of these sources. And what Hasura does is it maintains a metadata, which you obviously create and like manage and whatnot. And these abstractions are represented in Hasura metadata as models, as permissions, relationships across all of these sources. So all of your metadata is stored pretty much in, like, let's say, a bunch of YAML files, and then you have this representation of APIs as just models. In this case, for Elasticsearch, you will have collections and over multiple indexes, and you would have them represented as models, right? Hasura can also introspect and like suggest relationships across sources depending on what the constraints are. And metadata-based APIs have a very structured way to think about APIs, whereas when you're coding, there's lots more constraint, and we look at it in one of the further slides. But broadly, APIs as metadata is something which is pretty flexible, and pretty more structured. Whereas when you're doing code, doing CI/CD, or the pipeline will become a little bit more tedious. And again, there's an example here on the right, which represents like a model in Elasticsearch. You have like an orders index in Elasticsearch with a bunch of fields. And this is Hasura metadata for you, which tracks this model. And you can look at orders here with a bunch of fields like ID, date, order ID, and product IDs, right? So all of this adds up really well to reflect an API output. Now, the good thing is that since metadata is generic, the output of Hasura could be a GraphQL API or a REST API or any other format of API that you want to consume. So the good thing is that Hasura connects to your data sources, does some introspection, gives you these models to track, your commands to track for business logic. And you can obviously modify all of these data, and you'll be able to like create a good abstraction layer for generating any kind of output API. The good thing about this is also like there's the CI/CD automation is really easy. Prior to this, with whatever API that you've been building, lots of code level changes need to be done, and even testing requires a lot of code level snippets to do. Here, it's very much metadata driven, and the dependencies are pretty limited here, and you just worry about what metadata changes from one commit to another commit when you're working in a team, and conflicts could be resolved pretty easily as well. And deployments are also pretty seamless, right? So broadly, APIs are abstracted with metadata at Hasura. And this will lead to like creating like a semantic graph, right? And which brings me to the Supergraph layer, which is, so what does all of this now lead to? So you create subgraphs with Elasticsearch, you create subgraphs with another data source, let's say Postgres or your REST API. Now they're all independent. Subgraphs are all like different teams working on different subgraphs. So what does this all lead to, and what is the bigger picture here, right? Which brings us to the Supergraph layer, which Hasura is sitting in the middle, right? And what does a Supergraph here entail, right? There's a unified semantic graph that connects all your domains. So if you look at the bottom, there's a subgraph with Elasticsearch. Bunch of team members are working on this subgraph layer. There's another subgraph, let's say in Oracle DB, bunch of folks are working on this. And there's another subgraph, Mongo, or it could be another REST API. Right? So you have different teams working independently on these subgraphs, but then you also have cross collaboration between these teams, right? If you want data from Oracle to be indexed into Elasticsearch, you need some sort of collaboration at a schema layer or at a domain layer, right? So you need this collaboration to happen, but eventually you would want to expose all of this data cohesively into this one supergraph. And the reason why you want to do that is also you want a centralized place to look and manage all of your APIs. So one composable API, which you can use to like merge across all of these sources, or just independently query them as well. But then you have like one composable API to look at analytics, to look at who's accessing what, a good place to like do access control centrally, and then let all of this data come in from different sources, right? So, and one Supergraph also lets consumers access them pretty much easily, right? You have like account dashboards or your public APIs or internal apps, all of them accessing this one endpoint or one Supergraph powered by GraphQL in this case, which internally talks to all these sources. So distributed execution engine. So with Hasura, irrespective of what the sources are, it can proxy to the right data source efficiently with high performance. And I'll show the demo with the Elasticsearch case as well and how it's able to do it across multiple sources. But broadly, the Supergraph layer has a pretty solid, should have a pretty solid distributed execution engine that efficiently proxies or routes to various sources, right? Um, and finally, like federated ownership, uh, which enables all of these teams to collaborate on this unified API. So for example, if somebody on the Mongo team wants to collaborate with Elasticsearch or modify or add something to this, they will be able to then modify metadata of Hasura and then should be able to expose this to the Supergraph. Cool. So what does API automation now mean for Elasticsearch, right? You have like bunch of indexes in Elasticsearch, and the requirements are basically you want to standardize the API for data access. You want obviously to use the rich capabilities for any API. You would want like filtering, sorting, pagination, the ability to join across sources, so which is relationships, and fundamentally there are no relationships as a concept with Elasticsearch, but we'll see how we can join across these two sources, right? Because typically you have a join, SQL join, if there is like a database with SQL, but Elasticsearch technically doesn't have like a relationship within the same index. So you can also enable operators. We'll see special use cases where you have some text fields in Elasticsearch, and we'll see how you can enable some operators based on the subfields of those text fields. So when Elasticsearch indexes data, and especially textual data, it will also have subfields where it um, vectorizes or probably like does keywords for all of these fields. So you can also like do phrase matching or like sorting operators, enabling all of those operations on top of these subfields. And Hasura magically also like introspects those and then lets you enable those operators on top of that. We'll also see how easy it is to add new domain models. We'll add, let's say, 3 indexes to begin with, and then I'll add another index and then see how easy it is to quickly track all of this, right? And I'll also show you an example of joining across indexes, databases, and probably an external API if we have time. So, cool. I'll also showcase how Hasura is highly performant. And and with Elasticsearch, obviously, you query one index at a time. And for example, you have GraphQL query, which fetches, let's say, products data. You probably set up a limit, you do a var clause, probably do an offset, and probably even do an order by. The fact that this GraphQL query gets pushed down into Elasticsearch as a single query is where like it's basically the concept of query pushdown, where you're just compiling this GraphQL into this database equivalent query, which is in this case a JSON query that you would have sent to Elasticsearch yourself if you had written your own GraphQL server or your own REST API server. Right. So this compilation of whatever the dynamism of the query is, it will translate to the equivalent Elasticsearch query that you see on the right. We'll also see an example of how when there are joins across indices, how Hasura is able to avoid the n+1 problem. And because there's no notion of joins technically in Elasticsearch, we'll see how Hasura creates a list of data, which it passes as a filter to the second index when you're joining it. Right? So I'll show you the example of how it is able to do it and what the query exactly that gets hit into the database. So you'll be able to do tracing to see how performant the API is as well. Cool. Time for the demo. I will stop sharing and I'll probably change this to my code snippet, which is probably my entire screen. One sec. Desktop. Good. Yeah, I'm sharing my Elasticsearch setup here. So probably zoom in a little bit. Yeah. As you can see, I have like and this is the GitHub repo that I shared on chat. And I have like a few sample data here to start the Elasticsearch index. And what I'm going to do is I'm going to do Docker compose on this. Sorry, I need to go into this. I'm going to do a Docker compose, and we'll have this index up and running. Let's see. Yeah, so we have a health checkup running. There's an Alpine image, which is used to like index some sample data here. Cool. So we see that it's running on 9,200. So everything seems to be working. But let's verify that on the browser. Let me make a localhost 9,200. We can see that I'm getting the default Elasticsearch message. And also do an underscore mappings right now. And you can see that it is already indexed a few properties here. I can see there's a users index, there's a products index over here, and there's some logs index as well. So we already have some sample data indexed here, and it's already reflecting in my setup. Cool. The next step is let's now create a directory for creating a Hasura project. So I'm going to just say yes project. Sorry, this is make directory, yes project. Cool. Now I'm going to get into this directory. Cool. Yes. So the first step is we need to initialize a supergraph with the DDN CLI. So I'm going to do DDN supergraph init. And this is going to create like a bunch of files, and we'll see what all of these look like. I'm going to open up VS Code. Yes, those these errors. Cool. So when I did a supergraph initialization, I I've basically scaffolded this Hasura project. And you can see like a bunch of files here. But broadly, there's an app subgraph here. And there is like this engine, and there's like a bunch of global config, and there's env that you will also be filling in a bit. But this is the scaffolding of a Hasura Supergraph project. The next step would be to, let me actually clear this. Next step would be to connector init, right? And here we have a bunch of options. So we have connectors for all the popular data sources. And in this case, I'm going to pick and choose Elasticsearch. And I'm going to give it the same name, Elasticsearch, for this connector. And I'll let it pick the default port that it has suggested for the connector to run. In this case, it's 7662. And it requires an Elasticsearch URL in this case. So what I'm going to do is I'm going to give this local.hasura.dev 9,200, right? And in my Docker Compose setup, I already have the username and password set up, which is username is the Elastic username, and the password would be Elastic password. I don't have an API key for this setup, so I'm going to skip this. I'm also skipping the SSL certificates for this. And we don't need to give any specific index patterns. Hasura will be able to introspect all of that in one shot. Cool. So now we can see like a bunch of files have been created here. But let's look at that by heading to our VS Code setup. So we have a connector Elasticsearch directory that you can see here. It doesn't have too much going on here because we've just initialized it and we don't have any metadata yet about this. But you can see that the subgraph has now some environment variables being mapped. And we can see the env file and the root directory, which has like a bunch of values that we just gave as input including the Elasticsearch URL, which is my localhost instance. Seems to be a small issue here. Yeah, local.hasura.dev 9200, and then there's elastic password and username. Cool. So now everything seems to be fine. Let me do the next step, which is to introspect the connector. Now that we've initialized the connector, the next step is to allow Hasura to introspect. And I'm giving the connector name, which is Elasticsearch in this case. I'm asking it to add all resources, which will also automatically track all the models that exist in this Elasticsearch instance. Cool. So now we can see that it has loaded the subgraph. It has added a model for collection logs. It has added a model for collection products, and it's also added for our users. And it has generated these models, right? So let's go ahead and look at the configuration.json. So now we've introspected the database and we've generated some mappings here, which is so there is like a bunch of indices here. There's one for logs, which is some sample data. There's one for products with some fields, in stock, name, price, and product ID. So we look at that as well. And there's another index for users. And that's it, right? So we have three indices tracked here by Hasura. It introspected Elasticsearch and basically automatically tracked all of that. Right, so that's pretty good. So now we have the introspection step done. Now let's actually go ahead and start the build, which is to say we start the Docker Compose setup with the env file passed in, and it will basically create a watch of the changes that you have. So as you keep changing metadata, you should be able to see changes reflected on your Supergraph build. Cool. So now this is all started, up and running. A new tab. Let me go to Elasticsearch and ES project. We zoom in a little bit, and we need to now actually build the Supergraph. So far we've done all the scaffolding locally, but there's no build done yet. So I'm going to do a Supergraph build local. So this will technically actually do the build for your setup. Now it looks like it has built the artifacts for the engine. Everything has been built locally. So we're going to test this on a local URL and then see how this looks. So there is a simple URL that you can open up. This is localhost 3000. And this is the GraphQL interface that opens up for the connector. But here, what we're going to do is we're going to use the Hasura console to open this up. And here we see, so this is console.hasura.io, but then pointing to our localhost 3000 GraphQL endpoint, which is the endpoint that Hasura generated locally. And once we deploy this to cloud, this URL will become your cloud URL eventually, right? So that's setup. On the Explorer, you can see that you have like a bunch of indices that you can start querying now. So let me actually do a simple query which says app_logs. There's an ID. There's probably a host, level, message, and timestamp. So all the data that you want to fetch, and you can see that this index has returned this data. So you have an ID, host, level, message, timestamp, the same order that you have asked for. And there's just like 3 records here in this collection. Cool. So now let's actually verify how this query was executed in Elasticsearch. So we'll look at the trace for Hasura. And you can see that this is a query that went in. And you can start tracing the execution plan for this query and actually see which parts of the query are taking the most amount of time, and how do I optimize this, and where to optimize all of this, right? So now you can see all of this, and then maybe let me expand on NDC execute query, which will actually give me what is the DB statement that actually went in for this particular query. So you can see this is a post request, and this is a search operation, and this is the actual query that actually went in. Um, and this is typically your Elasticsearch query that you would have executed on your instance if you had to build your own setup. Now I'm going to test this with, let's say, Postman to see how this one looks. So let's do, instead of products here, I think we need a query for logs. And in my authorization headers, I have like the username and password configured. Uh, Ideally, in production, you'll be using an API key, and I'm passing in this query. So let me send this request, and we've gotten some hits back as a response. So this is typically what Hasura also executes and gets back data, and then it will pass in this hits JSON back as GraphQL response. So this is all working. This is all pretty straightforward so far. Now let's extend this to say, I want to actually add one more domain model, which is there is some orders data that I have, which are not part of this setup yet. So I have users, I have products, and I have some logs here. Now I want to also like start tracking orders. But before that, we can also like probably start querying products with filters. And let's say ID, let's say category, name, like this query. And we've gotten, because of the limit one, we've gotten one record here. So we have products. So let me now introduce orders into this model. But before that, I'm going to show you what that looks like. I'm going to go back to this directory, which is the Elasticsearch subgraph example. And open up in VS Code. And this is the orders data that I have. Now I want to be able to do a join between, let's say, orders to users, or user to orders, like an array relationship. And for that, I want to be able to link the user data the right way. So I want to query for users and then fetch their ID, their email, public name, just to ensure that everything's in place. Cool. So now I want to actually map these IDs that are there as part of the user's data into my sample data so that I'm able to like start tracking this. Want to modify this as well. This is user 2. The next one would be user 3. And we have user 1 already. So we're going to repeat this user ID for this last one. Cool. So now I have this orders data configured, and it is mapping to the user ID so that we can have the join set up. Right. So what I'm going to do is I'm going to index this into Elasticsearch using the bulk endpoint. I think this would be like a put request. And this is, yeah. I don't know if it's a post put or post. Let me try post. Yeah, sorry. Terminated by new line. Yeah. So now I have the orders index created as well. And to verify that, we can actually do like an orders search. And this will give us all the data that we just inserted back into orders with the user ID pointing to the user's data that we have indexed already. Cool. So now, obviously, this is not part of the API yet. So now how do I add this index into Hasura. So I'm going to actually do the introspection again. So I'm going to go into my project. I'm going to do DDN Supergraph. No, sorry, DDN connector introspect. Again, Elasticsearch and add all resources. And you can see that there's like a few updates to models, users, and logs. But then you can see that a new thing was generated for orders. This model didn't exist before. Now this is being created, right? Now let's look at the setup in configuration.json. Now you can see that there is an orders index being added to your configuration. So this is a connector configuration that is getting maintained here. Now let's go back to metadata and then see what's been added here. So you have logs, which has like a bunch of types here. There's an object type, there's metadata for permissions, there's some operator expressions that are defined here. And then this is the model for your index, which is the logs index in this case, along with the fields you see here. And then you also have model permissions. So you have type permissions and you have model permissions over here, which in this case, we only have defined it for the admin role. So you can start adding more role-based access control rules in this setup. Now this will repeat, this setup of metadata will repeat for each index, including the one that we just added for orders. So you can see object type, you can see type permissions here, some Boolean expression type with operators enabled for it. And then you have like the model for orders with fields defined for this model, along with the model permissions. Cool. So now we have this metadata introspected. Right. So now let's actually go ahead and build this locally. So I'm going to do Supergraph build local, and seems to have built fine. And since this is on watch mode, everything should have reflected automatically on our API. And we can see that this is already reflected here in our orders query. So you can start now asking for order, date, order ID, product ID, user ID, and whatnot. And we've gotten the data. So let's also look at the trace for this. This is again pretty simple. You have to go into the database query to see what exactly was sent. So we can look at database requests. And this is the query that's been sent for orders. And this is the orders search query. Right? This seems straightforward. So now let's move ahead with the relationship itself. Now we want the ability to now join across orders index and the users index, which exists separately at this point. So we have a users index here. And as we indexed orders, we ensure that the user ID value is actually the same so that you can use a common constraint to join. So we have this user's ID, which is common for the user ID value in orders index. So now the next step is to set up this relationship. So I'm going to go to Hasura metadata, and I'm going to go inside orders. Here, what I'm going to do is I'm going to use the VS Code plugin. So we have a Hasura VS Code plugin, which automates some of this step, or probably at least helps you scaffold the metadata pretty easily instead of typing this gigantic YAML configuration. So I'm going to do a kind relationship. So what I'm going to say is relationship, and it automatically already suggests is it a relationship to a command or is it a relationship to a model, and what kind of relationship is it? So I'm going to do a relationship to model, and you can see it has scaffolded the syntax for a relationship metadata. And I'm going to give it a relationship name. And just to recall, we are in orders and we want to be able to fetch the user data from orders as one-to-one mapping. So one order has one user. So we want to call this, let's say, a user uh, when we're querying in naturally from the orders collection. The source type here would be orders, which is the primary index here in this case. And target model name would be users, which is the target index, which is users. And the relationship type here is one-to-one mapping, in which case this is an object relationship. The other option would be if you are fetching orders data inside the user's collection, that would be like a one-to-many, which would be an array relationship, right? And then you want to like do the mapping of the fields. So you have the source field to map and the target field to select. So what does the source field here mean? The source field, so we are in the orders collection, sorry, the orders index, and orders has the source field called user ID, right? And the target is our users model, which is our target. And the field name in the users model is basically the ID uh, value, which we just copied for our sample data. So now I've created this relationship. I've filled in the necessary targets and the mappings here required along with the user relationship, right? So I should be able to now just do a local build and then restart this process. I've done a local build. Everything seems to have worked. Now let me go ahead and refresh this. And you should now be able to start querying, let's say, orders. Sorry, this would be, yes, orders, app orders. Let's fetch everything in this case. Let's say order ID, order date. We are worried about the user relationship. So let's make user ID, email, say there's an address as well, right? So now we're fetching a bunch of fields from the orders index. We have a bunch of fields coming in from the user index. And you can see that there is a relationship and there's a nested query within orders. I'm going to execute this query. And you can see that you have these details coming in from orders and you have the user data coming in as well as part of the relationship. Technically, this is a remote join between two indexes because there's no native joins in Elasticsearch. So we'll also trace how this query actually works and how is it highly performant here. So let's look at the trace, and there are two queries being made here, right? There will be one query. Ideally, we would want one query to be made for the orders collection, the index, and one query to be made for the user relationship, right? In a naive implementation, you would have made n+1 queries. For example, in this case, there are like 4 rows, 4 orders here. So you would have made one query to fetch all the orders and 4 more queries to fetch user for each order, right? Which is not an ideal case, but typically with a GraphQL implementation, unless you are doing data loader, you will be bound to face this n+1 issue. So the ideal use case is you make one query for orders, you make one query to fetch all the user relational data by passing in the relevant filters. Right, so let's look at the trace and then see how this happens. Let's look at NDC execute query. So this is the first query which is being sent to orders. So you can see that it fetches order ID, date, and user ID as part of the response. Pretty simple. This is the first query, fetches all the data in one shot. The second query is when you want to fetch the relational data from users. And we don't want to be making 4 different queries, and we want to ensure that this is batched into one request. So we will look at how this is done for the user's data. So now you can see that there is an aggregation query with a bunch of filters that's being sent here. So I'm going to copy this and just gonna go into Postman and do a users search. I'm gonna like fetch this, and you can see that it is fetching the user's data in one shot for the relevant filters. And the key bit is basically what the filters here are. So this is an aggregation. It fetches the ID, email, and address fields of your index. And you can see that the filters are getting applied in array in one shot. And there are like three records being filtered here. So you can see they are being applied to this data. And if you remember, orders had 4 records. There were 3 users, 3 unique users, which had to be fetched. And this is the filter that's being done to fetch those 3 users. And Hasura will basically mash up that data with the orders data to give you back the join data. So this is how Hasura is able to like avoid the n+1 problem. And this is exactly the ideal query that you would have sent to the database to fetch exactly what you want. So it is not fetching all the fields. It is fetching exactly the fields that you've requested in your GraphQL query. And it is also like doing it for one request per nested relationship. Right. So that's how Hasura is able to be performant and efficient about routing queries to different indexes. Now you can extrapolate this to other data sources as well. So you should be able to like set up a relationship not with just the Elasticsearch model, which is users in this case. You should be able to do this with, let's say, a Postgres model, which could also be called users or something else with a prefix. And you should be able to set up a source mapping field on what the fields are in Postgres and what the field is in Elasticsearch. And you should be able to do the same thing where Hasura basically is smart enough to send in one query to Postgres to fetch in, and then one query to Elasticsearch to fetch in data and then mash up before sending it to the client. So that's relationship and joins for Elasticsearch, and with regards to permission, you can see that we can see the Hasura role being admin here, and let's say I change this to something else which doesn't have um, the permissions configured. You can already see that the user is not authorized, right? And the reason is because we only have defined permissions for just the role admin. And let's say I add another permission to role user, um, which would be select, and let's say do a null filter again, just to ensure that this is allowed. So I'm going to do another build, and I'm going to do a restart. And it's still not be allowed. And I'm going to do just this. Yeah. So you should enable authentication outside of admin roles and pass in the right token. So you will pass in, let's say, an authorization token here. So you would do something like authorization would be a bearer token, could be whatever. And once you've defined that in your metadata, and once you have an authentication setup running, you should be able to now then join across this um, uh, permission rules, which currently has admin, but then you can add more role-based access control and then be very granular about which fields you will let access to. And all of that is configurable through metadata over here. As you start typing in, and VS Code will also suggest you what fields you want to filter on. But that's mostly what I had for today. And in the interest of time, I'm going to look at chat to see if there's anything else. And that's mostly it from my side. Feel free to post some questions on chat as well. I have linked to the GitHub repo already, but I'll also reshare this in case somebody else has missed it. There's the GitHub repo. Yeah. And of course, the recording for this will be posted soon. You'll all receive an email as well regarding that. But broadly, uh, this is the metadata-driven workflow that you would typically get with Hasura. We've seen Elasticsearch today. You can add more data sources in the same model, just a bunch of few CLI commands, and modify some metadata, build it locally, test it locally, and this metadata can be exported, can be just collaborated with other teams in Git, um, do CI/CD pretty seamlessly with this metadata, then keep collaborating with different teams. Now that you will own, let's say, Elasticsearch as a subgraph, another team could contribute to the same supergraph with, let's say, a Mongo or a Postgres or a REST API that they've been building. And at any point of time, you should also be able to start collaborating on the models between them. And nothing changes on the data source. Everything is at the metadata layer that Hasura has. So it should be fairly straightforward for the teams managing to not worry about changes internally, but then just change in the metadata layer, which lets you give the flexibility for the API and makes it easy to collaborate as well. Yeah, I think we are just on time. If you have any questions, feel free to put on chat, or I'm always available on Discord as well, so you should be able to reach out on Discord. We're also having an office hours running just now. It'll get started 10 a.m. PST, so you can drop in and probably even join there, and we'll see you there. If you have any questions, happy to do one-on-one chats as well. But yeah, that's it for my time. Sorry about the delay at the beginning, the technical issue. But yeah, hope to see folks around. Yeah, that's it for my time today. Thank you for joining.